Hi, in this video I'm going to show you how to solve symmetric tree, which is problem 101 on Leetcode. So I'll go through the description first, I'll talk about it a little bit, draw some diagrams, go through some cases, and once I have a good kind of high-level solution, I'll get to coding. It'll be written in Python, but of course you can use any language. The logic is what really matters. So let's get into it. So given a binary tree, check whether it is a mirror of itself, i.e. symmetric around its center. And they give us two examples of where it's symmetric and not symmetric. So let's look at these examples more closely, on the whiteboard. So if I were to put a line in between both these trees, and I were to flip one side over the other, they should basically match up. That's what symmetry is. So, the one thing over here is symmetric. Of course, one thing is always symmetric. These twos are symmetric, so i.e. the left child is equal to the right child. And then for these subtrees, the left child of this equals the right child of that. Therefore, these are symmetric. And the left child of this is equal to the right child of that. So there is kind of a pattern here that you can see. And of course, these are basically none. But when you have nuns, basically they're, I keep saying basically, but they're symmetric, right? None is symmetric, only one thing is symmetric. So we don't need to check past that. This tree, therefore, is symmetric. In this case, the one is symmetric. If I put a line in between, the left and right child are symmetric. However, if you look at the right child of this, there is no accompanying left child on this side. Therefore, this thing is not symmetric because there's no 3 here to make it symmetric. You don't need a 3, you also need a 3 here. So therefore, this is not symmetric. So let's now talk about specific cases. So if I, for instance, let me use white here. Let me talk about the simplest case. When there's nothing. When there's nothing, well, that is symmetric. If there's one thing, that's also symmetric. If there's children for this thing, it's something like this. And you have something on, let's say, again, something like this. Well, this is not symmetric, right? Because the left child exists here, but it does not exist here. Therefore, this is an example of asymmetry. And the last example is if their values are not equal. So for instance, if I had something like this, the structure is the same, but their values are not equal. Therefore, these are 4 different cases. So I think my idea here is what I'm going to do is I'm going to assume at the very start that my tree is symmetrical. And then as I go down, I want to compare, I'm going to look at the root and kind of check these two things. And then later, compare subtrees. And then I'll write a recursive function for this, and I'll keep going down. And if there's any, we'll do backtracking basically. If there's any false that pops up when I'm comparing the subtrees, i.e. comparing the left and the right of every child, then I know that the tree is not symmetric because I found one counterexample. And if I don't find that, then I'll return true. So that's kind of the high level logic. Let's get to coding. So let me first do the check to see, if not root, return true. And I've made this kind of function here called is subtree symmetrical, where you pass in 2 things, A and B, which are tree nodes, and it returns the same thing as the encompassing function. So let's first assume that this works, and let's just see how you would plug it in. So you basically call this function, and then you'd pass it root.left, root.right. And the first thing you want to do is check to see if A is none and B is none. And if that's the case, then we return true, because that means that, let's say if it was at root, there was no left and right child. They were both none. Therefore, you're done, return true. I could have also put this higher, but it doesn't matter. I could have called it over here instead of inside the function, but whatever. I'm writing all my logic kind of in here. So I think I want to check is make sure that if, you can do this in Python, so you can say if, else if not A and B, i.e. B exists and A doesn't exist. Or if you have A and not B, then what you want to do is return false, right? Because now the structure is different. the left child and the right child on 2 different subtrees. One of them is there, one of them isn't. The next thing I want to check is, now that I know these both values exist, I won't get a none error here, a none type. I can basically do something like this and check to see if their values are the same. If they aren't the same, then I'm going to return false. I found our counterexample. Otherwise, what I want to do now, I can just write a return now, is check to see if subtrees are symmetrical. And now check the left and right of that. And the other, for the other case where you want to check the other tree. So you want to check a.right and then b.left. Right? We're always checking the opposite. And we're going to return this. And if both of them are true, then this and statement will make them true and it will get passed up. And eventually, let me just move this out of the way so maybe it looks, it didn't get easier to read. Let me make this function, let me just call it helper so that everything fits on the screen nice and easy. Whoops, I pressed save. And we can put this up like that. So a.left, b.right, a.right, b.left. And let's see if this works. So that definitely works. Let me hit submit. I mean, I just checked one test case and we can see over here that is accepted. So again, we basically use no memory. We're just using a recursive solution here and it's just traversing through this and finding a counterexample. We're not storing anything here. It's completely stateless. However, it's kind of slow. Note that when you're using Leetcode, sometimes the box that you're running, this code on, every time you press run, it's finding some place to run this code. Sometimes that machine could be slow. So one time I had 28%, 28 milliseconds, and that was a lot faster. I think I hit like, I didn't tell me my distribution. I was at 93.54, but now I'm at 79.73. So again, it's the same exact code, but it ran a bit slower. So let's talk about time complexity a little bit. Again, there's no memory being here. There is a call stack that you're using though, because every time you're going down, you're basically making a new call stack, one for every subtree, and it'll get large, and that's kind of bad. I mean, if this is a really large solution, you probably want to do this iteratively, and maybe I'll do that in a future video. In terms of time, well, you're visiting and checking everything once, right? There's nothing more than that. There's no duplicate checks. So therefore, your time complexity is, if n was the number of nodes in this tree, your time complexity is n. So again, linear solution, but call stack is kind of rough. So that's how you do this question. I hope to make more videos to help you solve these problems. This was kind of an easy one, and it's kind of infamous, I think. Some people were saying, why would you ever ask us a Leetcode interviewing problem? Because that means you just need to know Leetcode. But otherwise, it's kind of fun. Stay tuned. Thank you. I'll see you in the next one.